and it should be on YouTube as well. So we have 2 sessions today. We'll have an introduction by Professor Deshika Narayanan, first up for half an hour. Then we have 3 talks after that. 4 talks after that, a short break, and then 3 talks after that. Please, if you weren't here yesterday, please familiarize yourself with the code of conduct on the CIDER website, and please abide by that as well. As succinctly put by Peter yesterday, don't be an asshole. Cameras and things will all be off, but if you're giving a talk, then you should be a co-host who you should be able to unmute and turn on your camera at will, but everybody else won't be able to, I'm afraid. Please keep all your questions to the Slack channel. So within the SIP CIDER channel on the Slack, on the Sazerac Slack workshop page, there are individual threads for every single question. So you can then post your questions within that thread, and then I will read them out to the speaker if we have time at the end of their talk. Otherwise, you can continue the discussion, much as was done yesterday. Lots of really, really great discussions going on within the threads on the talks and things. All of the talks are recorded, and so they will be available afterwards. So if you don't have, or if you have colleagues and things that aren't able to make it today, they'll be able to tune into those on YouTube as well. So for the speakers, at least for the contributor talks, you'll have 15 minutes. We roughly recommend that should be split into 12 minutes for your talk and 3 minutes for questions. I will play the following annoying sound, which hopefully you should be able to hear when you've got 2 minutes left. So I'll try not to say anything to interrupt your flow, but if you hear that, you've got 2 minutes left, all right? And yeah, I think that's all of the practical bits kind of sorted. So I'd like to introduce our first speaker. This is Professor Deshika Narayanan. So Deshika did his undergraduate work at the University of Florida, and then went on to do a PhD with Chris Walker at the University of Arizona. He was then a CFA fellow at Harvard from 2007 to 2010, and a Bock fellow back at Arizona following that. He then became assistant professor for 3 years at Haverford College, just outside Philadelphia, and then returned to the University of Florida, which is where he is now. So when you're ready, Deshika, take it away.
Okay, thanks a lot. And thanks so much for having me present at the Sazerac meeting. The Sazerac meeting series is a really fantastic one, and I'm glad that it's thriving so much. Okay, so I'm going to present a theoretical review of at least some aspects of gas and dust physics at high Z. Necessarily, I won't be able to cover all of it, but I'll do my best to cover some interesting topics. In specific, I'm going to break it up into 2 areas. One is dust physics and the other is cold gas. Within dust, I'll talk a little bit about the life cycle, extinction, attenuation, and in gas, I'll specifically focus on carbon-based chemistry. What this means is I'm going to leave out a lot of really interesting topics from a theoretical standpoint. So I hope you're getting a lot out of some of these topics from the other talks. Molecular outflows is obviously a huge one. One very important area that I'm going to leave out is nebular lines at high Z. But we have a number of talks coming up, and we had a very nice one yesterday as well. And unfortunately, I'll also have to leave out the first dust, but again, we have a lot of nice talks in that area also. Okay, so let's just ask, I'm going to break this up into 4 questions and try to go through these questions in turn. The first question is, what sets the dust content of a high Z galaxy in a theoretical context, of course? So this is how we used to model dust in galaxies, really until just a few years ago. I built my career on modeling dust in this way, which is you basically take the metal mass in your hydrodynamic simulation or your semi-analytic model of galaxy formation, you multiply it by 50%, and you say that's where the dust is. This is motivated by observations of galaxies both near and far. And so it's completely reasonable, although not as physical as we would like as far as describing the life cycle of dust at low and high Z. So I'm going to go through a little bit of the physics of what you might consider when developing such a model. This work, and really much of the work I talk about today, has been led by a graduate student of mine, Chi Li, who's graduating now and moving on to a nice fellowship at the MPA. So first thing we need to do is we need to form dust. So I have some cartoons on the right and I have some equations on the left. I don't expect you to internalize the equations by any means. They're just there to sort of try to describe some of the uncertainties in what we talk about. So dust can form in type 1, type 2 supernova and AGB stars. If we follow the Dweck formalism, which there are many formalisms to follow, this basically requires understanding what the elements are that are being ejected into the ISM, and then convolving this with some sort of condensation efficiency into dust. Dust can grow. This, as I'll describe, and as many of you already know, is an incredibly important aspect of dust evolution in a cosmic sense. So this just grows either through coagulation, that means dust particles stick together, or through the accretion of metals. These terms have uncertainties in them. There are threshold velocities by which we need to scale whether or not two particles coming together destroy each other or collaborate to form a bigger dust molecule. There are also accretion timescale uncertainties. These depend on the local densities, temperature, and metallicities. And so we have to set reference densities, temperatures, and metallicities in order to normalize these growth rates. And finally, and I just didn't have room to put the equations on here because I put Chi's picture on here, there are destruction mechanisms. There's thermal sputtering. Hot electrons in the hot ISM come and smash into your dust and destroy it. You can shatter, so it's the same thing as coagulation, just they come at a slightly different velocity. And there's estration, so destruction and star forming regions. So we can put these sorts of models into a cosmological simulation and ask the first question, what processes are important in setting the dust mass function? So what I've done here is I've run a very toy or baby cosmological simulation with all of our dust physics in it. But it's just a small 25 megaparsec cube box, just for the purposes of this this talk. And on the x-axis, I show the redshift. On the y-axis, I show omega dust for our model. So the full model is shown here. Dust grows. The dust mass grows over time. You expect that. Now let's ask what happens if I manually shut off growth. If I manually shut off growth, I lose orders of magnitude in my dust mass normalization. Growth is the most important aspect in setting the dust mass normalization in galaxies over cosmic time. What about destruction? Well, if I turn off destruction, just to give you a baseline point as to where we would be, that's where I would be. And now, out of the destruction processes, if I turn off thermal sputtering, we see that thermal sputtering dominates the destruction. So in other words, the best way to grow the dust mass function in your galaxies is through growth, through accretion of metals. And the best way to destroy it is through thermal sputtering, so collisions with hot electrons. The other processes are important for setting the grain size distributions, and I will talk about that. But in a global sense, these are the most important for setting mass quantities. This was confirmed by Ashwin Vijayan in a nice paper in 2019 using a completely different technique. This just plots the dust rates on the y-axis versus stellar mass. I forget which redshift this is at, but the top line here you see shows both destruction and grain growth dominating the dust mass functions. Okay, so where do we stand as a community when it comes to this? Because there's been there's a half dozen groups working on this. In one of the previous slides I listed a large number of the theoretical works that are working on this simultaneously. So just for this talk, I emailed a few people. So Gergo Popping, Ashwin Vijayan, Chi Li, and I emailed Luca Graziani. I actually apologize, I just didn't have time to implement his curves into this plot, but he did kindly send them to me. And I just asked, okay, so what if I asked you to isolate 10 to the 9 solar mass galaxies between redshift 0 and 6? And you tell me what's the dust to gas mass ratio? And then I plot the 1 sigma dispersion here. You see that broadly, in a cartoon sense, well, everyone agrees that we can get to dust to gas ratios about one part in 100 by redshift 0. And everyone more or less agrees at the epoch of reionization what they should be. But at cosmic noon, there are dramatic differences, orders of magnitude. Now, I just made this plot this week for this talk. I don't know the details of why exactly these differ. But looking into this just a little bit, I note two things. One is that there's differences in the galaxy formation physics that go into these models. So there's at least half a dex just in metallicities. Now this can proceed and this can impact the dust in a nonlinear manner because the metallicities at early times dictate what the growth rates can be like. At the same time, all of the dust physics is also very different. Dust to gas ratio measurements, as have been coming out recently with ALMA at redshifts 2 to 4, will be able to slowly begin place sharp constraints on the dust physics, especially if we can start to implement many different dust models into the same sort of semi-analytic or cosmological simulation to factor out any differences in galaxy formation modeling. Okay, question 2. What are the extinction and attenuation properties of dust at high redshift? Now, this is a topic that I get a little bit of a bee in my bonnet about over misused terminology in the literature. So I'm going to quickly school you guys on what extinction and attenuation both mean, because they are two different things. So extinction is a resolved property in the ISM where I look at a single star or a single point source, and I have a single line of sight a cloud in front of it. And extinction determines the absorption of photons or the scattering of photons out of your line of sight. This is most easily done in the Milky Way or highly resolved systems. What's more appropriate for the very early universe typically is the concept of attenuation. Attenuation is a more unresolved process where I fold in not only extinction, but also the geometry of my stars and dust. So I have scattering both into the line of sight, again, from other stars, as well as the contribution of light from unobscured stars that start to fill in my UV flux. The typical shape of an extinction or attenuation curve looks broadly like this, if you don't remember your graduate ISM class. It rises toward the UV fairly steeply, with oftentimes a bump around 2175 angstroms that is potentially due to PAHs, polycyclic aromatic hydrocarbons. Okay, so let's just conduct a numerical experiment. If I take one of our cosmological simulations and I say, well, I'm going to pretend like I don't know the extinction law. To first order, for many of these, we don't. And I'll assume Weingartner and drain for every single dust particle in this simulation. And I'll run dust radiative transfer to ask, what are the attenuation properties? And then I plot the attenuation properties as a function of redshift. I get something like this. So in the top left panel, we have redshift 0, redshift 2, redshift 4, and redshift 6. And these show heat maps of all of the dust attenuation properties in the SIMBA cosmological simulation. The pink line shows the median, and then the dash shows the 1 sigma dispersion. So the first thing to take away is that low redshift observers have a very difficult time. If they're going to do SED fitting or inference of physical properties, it's very complicated to know what your dust attenuation law ought to be. Luckily, as you get to the redshifts of interest for this conference, this dispersion goes down significantly and starts to collapse toward the extinction law. And the reason for this is that the stardust geometry becomes very simple at high redshift. And this is due primarily to optically thin conditions that we're able to get light to pass through the bulk of the galaxy very easily. So observationally, what are you going to do? How will we determine the attenuation law in the galaxies of interest, or redshift 6 or so? Well, one common way of doing this is through the IRX beta relation. We saw some nice talks about this yesterday. This is a nice schematic published by Gergo Popping a couple years ago, showing just from a modeling standpoint how different physical processes can impact where you are in the IRX beta relation. And except for the stellar population and age, which was really put forth nicely in a great paper by Naveen Reddy last year, almost all of these other properties, turbulence, dust screen with holes, FeV absorption, are all different ways of saying your attenuation law. So in this review article, Samir Salim and I wrote recently, we showed for a constant stellar population how different attenuation laws impact where you are in the IRX beta space. So the different red curves here show just different slopes of an attenuation law, marking off some places you might recognize: Calzetti, Milky Way, SMC. And then the blue dashed lines here show AV. And the main point of this is to convince you that your location in IRX beta space, again, holding a stellar population fixed, is dictated primarily by your attenuation law. So if you can determine the IRX beta relation in your galaxies, you could in principle determine your attenuation properties. Okay, so what are the results at redshift 6? This is a plot by Lichen Liang summarizing all high redshift galaxies and the one location. And the main thing I want you to pay attention to are these green and blue points here that were put out by Richard Bowens and Peter Kapak about 5 or 6 years ago. And as Denis talked about yesterday, many of these fall below the typical IRX beta relations we see for metal-rich galaxies at low redshift. So there's a few different possibilities where this could come from, and these are enumerated in the questions below. The typical explanation that is in the literature is that this is varying dust properties at redshift 6. That the underlying extinction law is different, therefore the grain size distributions or compositions are different, and that the IRX beta relation may be probing extinction because of optically thin geometries. There are two other possibilities though. One is that the attenuation law itself is varying. Li-Chen Liang had a very nice paper recently showing the evolution of some galaxies in the fire simulation. And basically when they come to the point when they might be quenched or at least approaching a post-starburst type phase when gas is being driven out, that they would fall below the tip of the local relations in IRX beta space. A third possibility, which was postulated by Richard himself in this 2016 paper, is that it's actually an observational effect. And primarily, in specific, this y-axis here has this LIR component to it, IRX, the infrared excess. So you have to know your infrared luminosity. Now, many of these data were taken in a single monochromatic far infrared or submillimeter point and inferring an infrared luminosity from assuming a dust temperature, a single 35 Kelvin, 40 Kelvin dust temperature and a modified black body. But if the dust temperatures at redshift 6 are much higher than this, then this would cause you to have significantly more infrared luminosity. And in fact, in our simulations and in many people's simulations, in Shencheng Ma's simulations and Li-Chen Liang's simulations, we see a strong rise toward dust temperatures at high redshift. So this plot just shows redshift 7 to redshift 2, and the typical dust temperatures in a series of zoom-in simulations that we ran a couple of years ago, but the same results are confirmed by other groups for different simulation types. That the dust temperatures get up to 60, 70 Kelvin at high redshift. And the reason for this is just the same optically thin geometries I was describing before, combined with harder radiation fields from lower metallicity stars. If there's an alpha enhancement of these stars, this will become even ever more so true. Now, there are some observational constraints coming out that are showing that there's a rise in dust temperatures at high redshift. This nice paper by Andreas last year showed this, but it's not obvious that the dust temperatures at redshift 6 are sufficiently high to match the theoretical models. So it may be that the theoretical models are predicting dust temperatures that are a factor of 50% too high based on the current observational constraints by Andreas. What about dust extinction? So I've talked a bit about dust attenuation. The physics of dust extinction is critical in determining what your attenuation loss will look like at high redshift. Now, the same sorts of simulations that can predict dust content with the right physics in them, and Shi Li has put them in very nicely into the simulations, has been done by Ryan McKinnon recently, by Hu and Hiroshita at Asia A have done a very nice job with this as well, in encapsulating the growth of dust grains by merging them together and the shattering processes, both of which can dictate not only the dust masses, but the dust sizes in galaxies. And the dust sizes are a critical component to determining your underlying extinction law. So as an example, we ran some cosmological simulations of Milky Way mass galaxies down to redshift 0 and plotted what the grain size distributions would look like. This is the relevant grain size distribution from Milky Way galaxies to redshift 0 and an MRN slope here. And you can see that the basic physics that we have that we think governs grain size evolution in galaxies reproduces what observations of the Milky Way give you right away. And so right away, we feel like we can maybe trust these sorts of simulations to now make predictions for redshift 6, 7, 8 and the JWST era. So what might we expect for these low metallicity galaxies at high redshift? So this is a busy plot, but I want you to just focus on this red boxed area here. On the x-axis is redshift, so this is today. This is very high redshift. And then the y-axis here is the UV to optical slope. So this is the slope of your extinction law. And this gray region here just shows the observed Milky Way region. So the basic idea here is that you have very steep slopes at high redshifts, at low metallicities, that eventually collapse down to a flatter slope. The reason for this is because as metals grow in galaxies, you end up shifting the power from very small grains to very high grains, to very big grains, just through growth processes in the ISM, just from accretion and coagulation onto dust grains. So the upshot is that in low metallicity systems, if I now collapse this into a plot that shows metallicity in these cosmological simulations as a function of extinction loss slope, or the other way around, you see that at low metallicities, we expect very, very steep slopes. Importantly, even steeper than the Milky Way or than the SMC. You know, if we take the sorts of metallicities that Ryan was discussing with us yesterday, a tenth, a little bit greater metallicity at these epoch of reionization galaxies, we can expect extremely steep extinction loss slopes in these galaxies. So these are some directions forward that I think will be important in the JWST era, especially as we start to think about dust in these systems. Okay, in the last little bit, I want to talk about two topics. One is, how do we determine the neutral gas content of galaxies? And finally, we'll talk about dust masses. So we've heard a little bit about some carbon yesterday, CO, C1, C2. We'll hear more about that today. And I wanted to go through what's everyone's favorite topic, interstellar chemistry. And in specific, in clouds and galaxies, what sort of carbon content do I expect? So I'm going to base this on CO. Let's just ask what forms CO and what destroys CO. The typical geometry we're going to assume here is a spherical cloud and then stars shining onto that cloud. So the basic destruction mechanisms are twofold. One is photoreactions. You could have guessed that. I have gammas that come in and photodissociate CO. They also photodissociate CH1, CH2, CH3, CH4, OH1, et cetera, which are primary formation mechanisms for CO. So Lyman-Werner band photons come in and destroy my CO. Another important aspect, which is oftentimes missed in literature, but was really popularized nicely by Thomas Bisbas a few years ago, is the importance of cosmic rays. So a cosmic ray comes in, ionizes helium. Helium's a hard atom to ionize, requires high energies, ionizes helium, then via a two-body reaction, I can destroy CO. The upshot is that in regions of high star formation rates, even if I have a lot of dust, cosmic rays can destroy my CO and turn this into C1 and C2. Okay, so this is modeling C1, C2 from neutral gas. What about ionized gas? Well, we'll hear more about that in talks later today by Vellini, by Young, by Karen Olson. But importantly, what matters is that we have to model carbon emission both from neutral clouds as well as ionized gas when it comes to C2 emission, because C2 has this annoyingly low ionization potential. Okay, let's ask the question now, how should we trace molecular gas? Well, I would argue, even though I think CO has built my career, CO is not the way to do this. There's a nice review article by Bellato almost 10 years ago now showing just trends in CO, the CO to H2 conversion factor, both with galaxy physical conditions that encapsulate the temperature and velocity dispersion that drive your CO emission profiles or luminosities, and with metallicity. The metallicity ones are just due to shrinking PDRs or growing PDRs, which I'll discuss shortly, in CO bright regions. So assuming that we find CO sufficiently uncertain, we might ask, well, what's happening in the rest of the clouds where CO is not illuminated? And this is CO dark gas. There are many models out there that suggest that the vast majority of gas in galaxies may be CO dark. These are the same sort of Milky Way simulations I showed you before by Chi Li, where we found something like 80% of the gas in the Milky Way has most of its power in C+, and only about 15% in CO1 to 0. This has been found by a number of other authors, by Munong Gong, who's a postdoc at MPA, Rowan Smith, by Padelis Papadopoulos, a whole number of theoretical simulations on simulations ranging from cloud scales up here and patches of the ISM to entire galaxy evolution simulations find that CO dark gas can dominate in many conditions, even in metal-rich Milky Way-like galaxies. Okay, so what about C2? Well, if we're not going to use CO, what about C2? C2 is a very viable tracer. This is just a nice rogues gallery of a number of beautiful simulations that we'll probably hear more about later today and that have been put out in the last few years. And indeed, C2 has been shown to correlate with star formation rate. This is just a bunch of different C2 star formation rate relations from varying literature models, from Katz, from Vellini, from Karen Olson, from Gergo Popping. And indeed, out of Karen Olson's group, David Visgen, who is an undergraduate, has directly modeled the C+ to molecular gas mass ratio and found a correlation between the two in simulations. So perhaps C2 is what we would use. I'll argue, however, that C+ does have some issues, some deficits, if you'll excuse the pun. And that's at very high luminosities, we start to see a deficit in C+ with respect to the far infrared luminosity, such that we start to see a breaking from the C+ star formation rate relationship. Now, there's many possible origins of this, and I'm not going to go through all of these, but I'm including this slide here so that in case any of you are interested in revisiting this, you can sort of examine many of these theoretical models that produce this sort of C+ infrared deficit. But one I'd like to focus you on is a family of models that basically suggests that this is due to shrinking PDRs. The basic idea is, imagine I have a cloud here that has no deficit, and it's just not notionally structured in CO, C1, C+. Now, if I go to very high surface density environments where I might be able to block out some of this Lyman-Werner photodissociating photons, I can build my CO and C1 reservoir and shrink the amount of C+ I'm getting per unit gas density and per unit star formation rate. And a number of different models, ours and a number of other people's as well, find that this naturally reproduces the C+ deficit, and it has the attractive aspect of being consistent with the correlations with sigma star formation rate that Justin Spilker, Tanya Diaz-Santos, and others have found in local and high redshift galaxies. An upshot of this is that it allows us to posit what may be an ideal tracer of molecular gas at high redshift, and this is C1. The reason for this is because C1 is a very stable atom in these spherical clouds. So what I've done is I've taken models of spherical clouds, and this is the inside of the cloud here, and this is the outside. And I've just increased the sigma gas in the presence of a radiation field. This orange line here shows where the CO profile is, so it increases toward the center of the clouds. This purple line shows the C+, and you can see as I go to higher and higher surface densities, I go to more and more CO dominated. That's this orange line here, and less C+ dominated. That makes sense. This gap here and here and here represents the C1 bright layer. And you notice that it's relatively invariant. It is the tail wagging the dog. Most of the gas is not in C1, but the layer, the fraction of gas that is lighting up in C1 is relatively invariant, even under dramatically different conditions from Milky Ways to ULIRGs. In simulations that we've run and others have run, we find, and actually I'm going to sort of skip this plot in the interest of time, but we found, and then Papadopoulos has found, Stellar Offner has found, Casper has found that the C1 to H2 relationship is maybe a very robust one. And I posit that this may be one of the more secure ways of determining an H2 gas mass at both low and high redshift. Okay, the final thing I want to talk about in the last couple of minutes is how do dusty galaxies at high redshift form? And if we have time, we'll connect them to Lyman alpha blobs. So, many people in this room are familiar with submillimeter galaxies at high redshift. There's quite a bit of interest. This very nice paper by Cassie Reuter et al. This last year at Illinois determined redshift distributions for submillimeter galaxies. And excitingly and relevant to this conference, the redshift distributions peak at very high redshifts, 3, 4, 5. These are extremely bright, extremely heavily star-forming galaxies that are critical for both the epoch of reionization through cosmic noon period. I see you, Chris. Thank you. So actually, I'm going to talk about your paper now, Chris. So I get an extra few minutes. So Chris Lovell, one of our conference organizers, and a number of us have run some simulations trying to understand the origins of these galaxies and cosmological simulations. This has been, you give an entire talk about how difficult this is to do in theoretical simulations. It's been a bug for theorists for 20 years now. Not a computational bug. It's something that bugs us. So this is just some mock maps that Chris made from the SIMBA simulations of dusty star-forming galaxies. These are mock 850 micron maps. These are redshift slices here, and then this is what the 2D map would look like at redshift 0. And we find, Chris found, excitingly, that these simulations very closely reproduce the number counts of high redshift submillimeter galaxies. So these are observed submillimeter galaxies from Jim Geach's survey. And these lines here show the number counts from the SIMBA simulation. Why is this relevant for this talk? Well, this is because this is deeply rooted in ISM physics. One of the important aspects of these simulations is that they include the life cycle of dust that I talked about in the very beginning of this talk. And in particular, if you plot what the predicted 850 micron flux density would be from these simulations, from radiative transfer calculations, using our explicit model for dust, as opposed to just what we've been using in the field for the last 10, 20 years, just a fixed dust to metals ratio, you start to see, especially at the bright end, factors of a few increase in the total 850 micron flux density. We're getting more dust out of these simulations. And at the same time, I don't have time to go into this, these help match the Redshift 2 dust mass functions being put out by Ian Smales' group, Alice Shapley, et cetera. So the dust physics may be critical in understanding these galaxy populations. These galaxies tend to have a wide diversity of shapes, sizes, colors, or morphologies. We see things ranging from giant spiral galaxies like Jackie Hodge has observed to pairs of galaxies that have not yet merged. So submillimeter galaxies appear to be a very diverse group of systems that, that are enabled by the production and importantly growth of dust in the ISM in metal-rich environments from the highest redshifts through redshifts 2 to 4 when we observe them. In the interest of time, I don't have time to really go into the possible connections with Lyman alpha blobs. So I'm going to sort of skip past this and go to my concluding slide. I've discussed a few areas where we've seen progress in dust and ISM physics and galaxy formation simulations. I'd like to talk a little about, just briefly, about where I'd hope to see areas go in the future. With dust, I think PAW physics and the origins of the first dust are critical. These represent wide open areas that we don't know nearly enough about, especially in the area of JWST. In the area of coal gas, I didn't discuss this, but I feel like a very important area to go forward in is nebular line emission and robust metallicity indicators at high redshift. We heard quite a bit about this yesterday from Ryan, and we hope to hear some more about this later today. And I think this area is ripe for future progress. Thank you.
Thanks very much, Deshika. There's a number of questions already on the Slack, so I don't know if you can see those already, but I'll read out just the first few. We currently only got a couple of minutes left for questions, but we're supposed to have a 5-minute break. So I'm just going to overlap with that a little bit, but if you need to go and make a cup of coffee or whatever, depending on where you are in the world, it might be something stronger, then please feel free to. So the first question is from Denise Bergarella. Says, thanks for the nice talk. About the dust, you talked about some variation of the slope. This slope can vary for several reasons that include non-independent parameters like grain composition, age of the stellar populations, stellar yields, etc. What is your take at the main origin, if any, on that? So that's the question one. And then the follow-up question is, what do you assume about the UV bump at 217.5 nanometers? It can move galaxies in the infrared versus beta diagram.
Okay, great questions. I'll tackle the slope one first. And these need to be broken up into attenuation versus extinction. So with attenuation, my personal opinion, although I don't know that I can necessarily prove that immediately, is that the stardust geometry is what dominates, especially in massive galaxies. Certainly in our simulations, that's been true. And I actually asked a graduate student who is collaborating with me, Sydney Lauer, to investigate this a little bit in our simulations recently, just to build some intuition, to change the extinction law manually in our simulations and see how that changes the attenuation slope. And certainly it does impact the attenuation slope, but the dispersion in what you see at a fixed redshift remains roughly constant. My hope was that you could use the attenuation law to determine the extinction law, and at least from the simulations, we determined we could not. With extinction, the slope appears to be correlated with quite a number of things, both with the metallicity, but one thing I didn't talk about is the grain composition. The grain composition, whether they're graphites or silicates, determines quite a bit what the actual optical properties and thus extinction law will look like. And so that can be nearly as important as the metallicity itself. And so in that area, there's quite a bit of open room for modeling progress and understanding how that impacts the slopes of the attenuation loss. We make some assumptions, assuming drain and Leor optical properties, but there are many different dust models one could assume. So I would say that is quite uncertain. I've forgotten the IRX beta question as I spoke.
I think we'll just quickly move on to another question, if that's okay. So you
I can answer
reply to Denise in the Slack. Yeah. So there's just one quick question. It's got a few upvotes from Laura Slavigo. Thanks for the nice talk. 2 questions / comments. 1, do you think growth plays an important role at very high Z? What are the timescales for such growth? And then the second question is the plot that you showed by FACE 2020 features the
frozen or you're frozen.
Oh, sorry.
Sorry, we're running a bunch of Zooms here, so I may be frozen.
Oh, okay. No, I think you're okay at the moment. The plot that you showed by FACE features the peak dust temperature. This value in general differs from that obtained from the SED fitting and the physical temperature of dust. What is your take on the evolution of the physical dust temperatures at high Z?
Great questions. Okay, so I'll try to tackle them quickly. So I don't know as much about how important growth will be at high redshift, at redshift 6, 7, 8, because we're starting to just look into these simulations now. The aforementioned graduate student, Sydney Lauer, is actually exploring this now. My gut feeling is that it's very important, and I hope that Luca talks a little bit about this later today in his talk. With the, what was the second question? Sorry, what was the second part of the question?
The peak dust temperature.
Oh, peak dust temperature, right? Yeah. So so I think the physical dust temperature is actually quite different from the peak of the SED. The peak of the SED is just hitting the tau = 1 surface, and in our models, the peak dust temperatures can easily be hundreds to hundreds plus Kelvin, especially in starburst environments, in SMGs, and in low redshift ULERGs. These things can get very hot. And in fact, that ends up driving many of the aspects of the CO to H2 conversion factor in our models due to coupling with the gas. So at least in our simulations, I think the dust can be quite hot physically, even if that's not translating to what you observe.
Great, thanks, Deshka. I think we should leave it there. There's now just a couple of minutes, maybe a minute and a half, to quickly grab a refreshment before we move on to the next talk. Which will be by Casper Elmheitz. So if you want to get your slides ready, Casper, feel free to.
Yep, will do. Right, hope this is still all right. Sure.
Yeah, it looks fine to me. We'll just give it another minute or so. We'll
definitely
need to come back. Okay, we should probably get started. So Casper's from the University of Iceland, going to talk to us a little bit about constraining the C1 and CO to H2 conversion factors at Z greater than 2 from absorption selected galaxies.
Yep, thank you very much. So first I would like to thank, of course, the organizers for hosting this great mini online conference. It's been great with a number of great talks, and I'm happy that I got a chance to share some of the stuff I've been working on lately. My name is Casper, and I'm currently at the University of Iceland, and I'm one of the imposters here, this theoretical session, working mainly on observations. And today I'll present some of the stuff I've been working on to try to constrain the C1 or O to H2 conversion factor directly in high redshift galaxies. So just to give you a brief background, so what you typically do is that you measure, at least at high redshift, you try to measure the CO emission lines, and you can also measure neutral atomic carbon, C1. And then what you need, because that's only a very small fraction of the total molecular content of these high redshift galaxies. So what you need is a conversion factor translating your CO or C1 measurements into H2 abundance or H2 mass. So in the Milky Way and in some nearby galaxies, you can measure directly the virial mass of the molecular clouds, which you can then relate to the observed CO luminosity, for example, shown here in the left plot. And so fortunately, we have there's a number of different environments where you can measure this. So we also, as Jessica showed in the last talks, there's this metallicity dependence, surface brightness, surface density dependence, and so on. But ultimately, it's still only possible to measure this directly in the very local universe. And then, of course, there's this elaborate theoretical framework also supporting it. But what we're really interested in is to verify that these conversion factors, they actually hold and these relations, they hold at high redshift as well. But fortunately, emission is not the only way you can detect molecular clouds at high redshift. You can also detect them in absorption. So this could be either from a gamma ray burst exploding somewhere in its host galaxy and then propagating throughout the interstellar medium of its host. You can also imagine a bright quasar located behind a foreground galaxy that then shines through it, and then if it intersects a molecular cloud, can tell us something about the composition of this molecular cloud. So this is shown, this schematic at the bottom, where we can actually very accurately measure the H2 column density and then also the C1 and CO column densities of the molecular cloud in this line of sight in absorption towards these bright background sources. And then just to show you an example of what that might look like. So here's an optical afterglow spectrum of a gamma ray burst called GRB 181020A, which shows, first of all, so if you look at the bottom to the left, this is a very broad Lyman alpha H1 absorption feature. And then there's a bunch of these very narrow features, which comes from the H2 Lyman-Werner bands. And you can see, so it's plotted, zoom in on the top. And then also to the right, you can see an example of some of the absorption features we observed from neutral carbon. And then you can see we can actually determine the column densities of each of the excited states of neutral carbon. In this case here. So the reason why I'm focused on C1 in this talk, which I'll just pretend that it was all based or motivated by Jessica's nice talk showing that C1 may be the best tracer of H2, but ultimately it's because we have only detected CO so far in one gamma ray burst and then in a handful of these quasar selected absorption galaxies. So the reason why we focus on C1 for now is basically just because that's where we have some data points. And what we are interested in is to derive this alpha C1 conversion factor, so the molecular gas mass to the C1 luminosity. So what we do is that we directly measure the column density of C1 in the first excited state, and then we can calculate the expected line luminosity per unit column in this line of sight by assuming spontaneous decay rate, which gives us this luminosity on the left side, and then on the right side we can of course also measure or determine the H2 mass in the line of sight. Then we multiply that by some constant scaling to account for helium, which allows us to write this expression for the conversion factor in the line of sight between the expected C1 luminosity and the molecular gas mass. And then what you can do is that we know that that the ratio you observe in the line of sight represents somewhat the mean of the actual density ratio throughout the galaxy. So if we use that and then use some unit conversion, then we can get an estimate of the actual, so the global C1 to H2 or C1 to molecular gas mass conversion factor, simply by just using the ratio of the column densities of H2 and C1. And then when we do that for a number of systems, and then we get the following points. So here the red points, those are from these absorption selected galaxies where we have a gamma ray burst shining through the hosts. then the blue points are from absorption-selected galaxies foreground to bright quasars. And what you can see is that they follow a very nice anti-correlation. So on the y-axis, that's the alpha C1 conversion factor, and a very nice anti-correlation with increasing metallicity. So you also get a very precise metallicity measurement in the line of sight to most of these galaxies. And then when you compare to some of the theoretical expectations from Glover and Clark in 2016, so they're shown for different interstellar radiation field strength, you see a very nice correspondence between these these simulations. And also there's a recent study by Crocker et al. Determining the C1 to H2 conversion factor in nearby galaxies, and our solar metallicity estimate is perfectly consistent with that. And then also I just want to note that all these points, so all the red and the blue points, those are from absorption selected galaxies between redshift 2 and 5. So these are all done at high redshift, these measurements here. All right, then what we want to do so because from absorption itself, we can only say something about the line of sight relative abundance. So we can only say something about the relative fraction of C1 to H2, but we don't know anything about like the global luminosity or the total integrated luminosity and the global H2 mass. So what we need to do is that we need to apply this new calibration or conversion factor to C1 measurements. So we used a sample from Valentino et al. From 2018. Which also had CO measurements. So I think it was CO 3:2 or 2:1 transition, which we then use to estimate on the x-axis the molecular gas mass using typical alpha CO conversion factors, and then compare to our alpha C1 conversion factor on the y-axis. And if you focus on the colored points, which are color coded according to metallicity, so we use a metallicity dependent alpha CO and then also this metallicity dependent alpha C1 relation. And you can see there's a perfect match between the two methods over 3 orders of magnitude here, demonstrating that this method, this absorption technique is quite good or quite reliable at inferring the molecular gas masses. And then adding also to the stuff that Jessica mentioned, that C1 in itself actually might be an even better tracer than CO of the total molecular content. All right, and then just as a small teaser, I want to mention that it's actually also possible to estimate the C2, so the fine structure C2 transition in absorption. And we also showed before in the spectrum, the H1 column density. So using a similar technique, we can actually also measure a conversion factor between C2 to H1, which allows us to estimate the H1 gas mass of individual galaxies based on the C2 luminosity out to redshift of 7, and also allows us to estimate this H1 gas mass density shown here between 4 and 6, based mostly on the new Alpine data, which seems to confirm previous results based on DLAs. All right, and then just giving a short summary overview. So what we can do at high redshift is that we can't detect the H2 emission, or we can detect the emission from H2, but we can detect it very nicely in absorption. We can detect CO quite easily in emission, but not so much in absorption. And then C1, there's these increasing number of C1 dissections, both in emission and absorption. And there are these other various molecular gas phase tracers that you can also use. But then importantly, so in emission, you get this total integrated CO or C1 light from the galaxy, where in absorption, you only get this single line of sight. So we don't know anything about the total content, but we can very accurately determine the relative abundance through the line of sight, which you can then apply to these global measurements to infer the global content of molecular or H1 gas. Great, so that brings me to my summary slide. So in 10 to maybe 20% of these GRB afterglow or quasar spectra, we detect molecular hydrogen in absorption, and we can determine the line of sight column density. And that makes it possible to infer the C1 to H2 conversion factor directly in high redshift galaxies and as a function of metallicity. So if you remember from the plot I showed previously, that we can actually do this from metallicities ranging from solar to maybe 100th of solar metallicities. So a very broad metallicity range, much broader than we can do in the local universe. And then we can apply this conversion on these global or total integrated properties that we observe in emission to determine the total H1 and potentially the total H2 and potentially also H1 gas mass. Right, so that was just leave this up here.
Thanks very much, Casper. Please post any of your questions in the thread on Slack. Got a few minutes for questions. So we have one come through now by Shenki Yang. Why alpha C1 is negatively correlated with metallicity?
So this basically just shows that, so for low metallicities, you have a larger H2, or yes, you have a larger H2 content per unit C1, right? So more H2 per C1. So you expect similar to CO, you expect this for higher metallicities, you expect the CO and also C1 to build up in the molecular clouds. And also, I mean, so this is also purely a metallicity effect in that you have an increased carbon. So for 1 unit of metallicity increase, you also have a 1 unit increase of carbon, more or less. So it's like a combined effect.
Okay, great. Thanks. Got another quick question from Ramil Dabe. Are you concerned about covering factors and saturation when measuring the columns of H2, C1, etc.?
Yes, in some sense. I mean, so you can see there is some extreme outliers in this plot as well. So you definitely expect there will be some cases where you intersect like the very most outer region of the cloud. So you only detect H2, for example, or you detect a very dense region where you have more C1 or CO compared to the typical. But I think on average, so we need a detection of C1 in the first case. So we know you're intersecting somewhat close to this to the inner layers of this molecular cloud, and then we just calculate the fraction, right? So if you intersect. So if you still detect C1 and you intersect close to the center, then you will have both a larger line of sight abundance of H2, but also C1. And then if you detect it further out, you just have lower amounts of both C1 and H2. So the fraction should more or less be, on average, consistent.
Okay, great. Thank you very much, Casper. We'll move on to the next talk. Feel free to also add any more details on the Slack channel, Casper, or any further questions as well. Yep. So now moving on to check the Livia Bellini.
Yes.
So if you could just share your screen.
Is that okay?
Yep, that's fine.
Very good. So Thank you very much for having me during this fantastic meeting. And I'm really glad to have the opportunity of presenting this work that I've been doing with the collaborators that are mentioned here concerning the surface brightness ratios in O3 and C+ in the EOR, and how this is connected to the burstiness of a galaxy. So before going into the detail, I just want to provide a really brief motivation. So why do we care about these lines? Why are so powerful? Essentially, if we want to understand the impact of galaxies during the epoch of reionization, we must definitely shed light on the internal properties of such sources, and meaning the ISM properties, so the gas density, the turbulence, the metal enrichment, and so on and so forth. And moreover, how these impact the way in which they convert the gas into stars, and so they produce ionizing photons, which then have obviously an impact on the reionization process. So with ALMA, obviously, we have we started really opening a window on the ISM of early galaxies on sub-kiloparsec scales, and this is because ALMA has a very unprecedented spatial resolution, but it's also targeting lines in the rest frame far infrared that are not really affected by the dust extinction, and in particular, the C+ and oxygen 3 have a huge diagnostic potential because they yield a complementary view of the ISM at early epochs, tracing the C+, mostly the neutral molecular gas, and the oxygen 3, the ionized gas. Here I just show really just a collection of the current joint oxygen 3 C+ detection in the redshift range between 6 and 9. So we have like 9 galaxies for which we have both detection, but some very peculiar properties are emerging. First of all, concerning the luminosity ratios between the oxygen 3 and C+ line, because we see that the ratios in these high redshift galaxies are on average higher with respect to what is reported in local star-forming galaxies, including local dwarf galaxies that are supposed to be good local analog of EOR galaxies. And this has been discussed by Aricane, Arata, and also Carniani, from which I took this plot. And the other characteristic is that the C+ is 2 times, up to 2 times, and even more extended than the oxygen 3. So like we have to pay attention in extracting the flux and possibly correcting if the flux is missed due to the angular size resolution of the observation. So another possibility is to go and try to push further our analysis of the oxygen 3 versus C+, focusing on the surface brightness ratios, so that the different extension of different emitting region can be in some sense accounted for, and moreover, and most importantly, because these ratios are more closely related to the local ISM condition, and also to this together with the star formation rate surface density, than the integrated value of oxygen 3 and C+ line. So in a work that, well, is in preparation, but actually is ready to be submitted, we computed the oxygen 3 over the C+ and the C+ surface brightness for the galaxies that I was mentioning before, and also seeing that in comparison to single patches in the ISM of local dwarf, we recover again higher ratios in the oxygen 3 over C+. We also tested and like compare this calculation with results from simulations at redshift 7, both at the original resolution of the simulation and accounting for a possible effect of beam smearing due to different angular resolution. And what we find is that, yes, there is an effect due to the possible dilution of the flux to the observational like capability of of ALMA in this case, but the ratio keeps being more or less already like fixed. Another possibility that we explored is how this connected with the local patches in the ISM of galaxies. So we extracted, as you can see in the crosses in this plot, the C+ versus oxygen 3 surface brightness, and we find that actually high surface brightness ratios are not due to observational bias, but really they arise from the extreme gas condition prevailing where there is the peak of distribution of patches in the ISM of early galaxy. To understand better the physical mechanism causing this behavior, we also used an analytical model, which has been presented for the first time in Ferrara and collaborators in 2019, and also extended in a work that we published last year in which we included also the surface brightness of UV line, and has been also extended to oxygen 388 micron. And this analytical model essentially relates the surface brightness to 3 parameters. The first one is the burstiness parameter that describes the deviation from the Koenig-Schmidt relation. Then there is the gas density and the gas metallicity. I'm gonna just showing a very simplified sketch of how this works, how the KS relation, a possible deviation from the KS affect, for instance, the C+ line. If a galaxy is a starburst galaxy and so deviates from the KS and has a factor KS above 1, then the starburst produce larger ionization parameters or higher Iden fields, and these produce higher column densities in the ionized gas and lower PDR column density, decreasing the C+, while the opposite is true for the oxygen 3. Obviously, there are degeneracies, and this is due to the effect of density, as shown here just for the C+ with the sketch. And also due to the metallicity, again, because these affect also the possibly the dust-to-gas ratio, which generally scale with metallicity, even though there are obviously uncertainties in this regard, and so the penetration of far-B photons. So if one has three observable, then can, with, for instance, an MCMC algorithm, derive the posterior distribution of the gas density, the deviation from the Smith-Kennicutt relation, and the gas metallicity. And this is what we have done for the sample that I was mentioning at the beginning of this presentation. And what we found, and are just three examples among all the galaxies that I was mentioning before, is that now I want to focus especially for the best fit KS parameter that I was explaining before. This parameter is pretty high, is up to 100. So this points toward oxygen 3 over C+ emitter in the OR being starbursting galaxies with really upward deviation from the Smith-Kennicutt relation. Moreover, these imply a very short depletion time in line with spatially resolved measurement in dusty star-forming galaxies, which are completely different environment with respect to these high, like up to Redshift 9 galaxies. Another result is obviously the prediction on the metallicity of the galaxy, and we have we had the opportunity to compare our results with those obtained by other works by Jones and also Younger, which will give a talk in I think half an hour. And we find that more or less we are in agreement that the metallicity is already pretty high, or not super low at Redshift 9, between 20% and 50% solar. And also the gas densities, apart from two outliers, which are more or less at a density 10 particles per cubic centimeters, as shown in the right panel here. We have some of these galaxies which are pretty dense, and so this, together with the metallicity, points toward an ISM that is dense, fairly enriched, and really bursty, and so this is probably the major impact of the properties of the ISM on the star formation in these very distant galaxies. Finally, we also studied we try to marginalize over the three parameters, searching for the relation between the surface brightness ratios and the Barsness parameter, finding more or less a linear relation and a positive correlation. And also we analyzed the separate effect of density, of the gas density, finding a decreasing trend. And this is something that we explain because if the density of the average density of the galaxy is above the critical density of the oxygen 388 micron, then the other line, the 52 micron line, is favored, and so the oxygen 3 over C+ ratio goes down. If you are below the critical density of the oxygen 388 micron, then you see that the density doesn't matter very much, and what really make the difference is the deviation from the Smith-Kennicutt law. Obviously, we were also interested in assessing the effect of the metallicity, because we expected that the low metallicity galaxies are bright in the oxygen 3, but we didn't find any straightforward relation between the surface brightness ratios and the metallicity. And this is so this highlights that really spatially resolved studies and pushing for high resolution observation can really help maybe in disentangling also the metal enrichment in different patches of the ISM. So before concluding, I just list here what are the main take-home message of this work. The first one is that these joint oxygen-3 C+ emitters are characterized by ISM conditions that favor an efficient conversion of gas into stars. We find the relation between this Ks parameter and the oxygen-3 over C+ ratio, and we do not observe any straightforward relation with metallicity. Also the metallicity and gas are pretty high, and so I conclude here and I take your questions. Thank you very much.
Thanks very much, Livia. Just waiting for a few questions to come in. So Ashwin has a question. Nice talk. Do you expect C+ and O3 to be co-spatial and thus have an effect on the drawn conclusions?
Yes, this is a very good point, and I forgot to mention, but yes, so there are obviously some of the sources that I was mentioning are actually show a displacement between the oxygen-3 and the C+, and this has been observed and has been interpreted as an effect of maybe star formation feedback and things like that. So obviously this model being like an holistic model, like using a few parameters to try to understand what is going on average in the ISM, cannot include this information because we would need another parameter, so another more uncertainties. But yes, this might be like a caveat to be taken into account when obviously analyzing in this way the data. So I totally agree that this is a good point. So going to high resolution, possibly like would that obviously not 100 parsec scale such in simulations, but we'll see.
Great, thanks. Another question from Ryan Sanders. Does your model assume the same density in the H2 and PDR regions?
Yes, but we also yes, because we assume this essentially a single slab model with a fixed density, and so yes, the answer is yes. But we are also planning to include some kind of clamping factor in the model, but this is deferred to future like improvement. So at the moment, yes, this is the assumption.
Yeah, so his follow-up to that was, is this justified given the very different regions and temperatures of the O3 and C2 emitting regions, C+ emitting regions? So
sorry, the temperature or the density? I missed
given the very different regions and temperatures of the different O3 and C+ regions.
So for the temperatures, there is like the model that compute the C+ and the oxygen-3 takes into account of, we derive the column densities assuming different temperature, like the abundances and the emission, assuming that the PDRs has a temperature of 100 Kelvin and the H2 region is 10 to the 4. So we do not assume the same temperature, obviously, in the two regions. This is not an issue. For the density, the only thing I can say is that in the simulation, the zoom-in simulation, we do see H2 regions that are very dense. Okay, so we are also investigating like on the simulation side, and yes, I agree that generally the H2 region are a little bit less dense than the PDRs, but according to the simulation we have at the moment, we see that everything is pretty dense in the ISM of the galaxies, that actually 7 point something that we have from the output.
Yeah, there's a quick follow-up question, I guess, related by Karen Olsen about whether you're showing mass-weighted density and the differences between low Z and high Z. I think we've just run out of time, so if you don't mind following that up on the Slack channel,
sure,
that'd be great.
Sure,
But,
I'll go immediately.
Great, thanks very much, Livia. And Karen is actually up next. Karen Olsen. I'm not sure if she's actually been made a co-host. Ashwin, could we sort that out quickly? Yeah, sorry, Karen, you have to be a co-host first. So just gonna set that up and then you should be able to unmute and share your screen. Okay, yeah, try now.
Hi, Karen.
Great.
Can you hear me?
Yep.
Okay, thank you. Yeah, I went out for a brief second, so that's why I lost my co-host rights.
Gotcha. Okay, we can see that. That's great. So this is Karen Olsen from the University of Arizona, going to talk to us about Sigame.
Yeah, thank you very much for letting me speak at this wonderful meeting. So I'm a postdoc at Arizona, and I'm funded by NASA to look at archival Herschel data and using my module Sigame to analyze that data. So Sigame stands for Simulator of Galaxy Millimeter and Submillimeter Emission. And I'm working with these amazing people. And we just released a new version of Sigame version 3 that you can read more about here. There's also this, let me get a pointer, new release of the code that's still being tested, but it's all out there. So I know it's a good idea for a 10-minute talk to only have like one takeaway, but I couldn't decide. So I'm going to show 2 examples of using Sigame at the Epoch of Reionisation, and then just a sneak peek of this new version of Sigame. So the first thing I want to talk about is line intensity mapping. As most of you know, that is a very exciting method of mapping in 3D faint sources and the intergalactic medium at high redshifts for very large patches of the sky. So like Kirsten said yesterday, ALMA is showing us far infrared line emission from galaxies during EOR, but it has a very small field of view. So these experiments will be able to really map out large volumes. On the theoretical side, we want to be able to make predictions for these experiments and later use the models to interpret the observations. And there are basically like 2 theoretical approaches that I'm using the convention of this review by COVID's 2017, dividing them into phenomenological approaches, building upon empirical relations between, for instance, line intensity and SFR, or line intensity and dark matter halo mass and redshift. The other one is using a local environment approach. So sort of from bottom up, make a model for galaxy formation and in post-process calculate the line emission. So typically that's been done with semi-analytical models or SAMs to get a large enough sample. But I'm going to show an example using cosmological numerical simulations of galaxy formation. First, let me just briefly go through the version of Sigame that was used for this result, just to give you an idea of what goes on under the hood. So Sigame takes the galaxy output from a logical simulation. For this, we were using SIMBA, which has gas described by fluid elements, and we extract these properties that we're interested in, position, velocity, mass, temperature, metallicity, smoothing length, and H2 molecular gas mass fraction. And then we combine that with the stellar info to estimate the far UV fields locally using Starburst 99. We also use this molecular gas mass fraction to divide the ISM into molecular clouds with a GMC mass spectrum and diffuse gas that can be either ionized or neutral. And then for each of these very broad ISM phases, we used cloudy models to interpolate for the line emission and then convert the results into spectral data cube for analysis. So Daisy Leong came to me as a grad student, and what she really did was to speed up the version 2 of the code by making some parts of it parallel, and she was able to apply it to roughly 11,000 galaxies during EOR using 3 simulation boxes from the SIMBA simulation. And she was really interested in the C2 luminosity function. And she showed that, well, these 3 boxes actually agree pretty well when we do this whole post-processing scheme. And we're also in agreement with the results by Popping 2016 and 19. However, all of these theoretical models, we have the same problem of reproducing these very high C2 luminosities caused by very star-forming galaxies that just are hard to find in cosmological volumes. So that's still an issue we need to look at. But what I wanted to really highlight that has to do with line intensity mapping is regarding this first phenomenological approach of using halo mass to estimate C2 luminosity, Daisy actually plotted the luminosity that she gets as a function of halo mass, just taking the central galaxy and its halo mass. And we see quite a lot of spread. She did this binned mean and fitted it with a prescription from Silva 2015. And we can do that, but there is this scatter simply due to all the parameters that we're including, like metallicity, SFR, molecular gas mass fraction. But that raises the question, can C2 be parameterized if we're using more dark matter halo parameters like shape or merger history? So that's something I really want to look into, and also look at other far infrared lines, because a lot of the experiments that I listed above are for C2 and CO, but we could also perhaps imagine using something like O3 as a mapping tool. Okay, the other application of Sigame that I want to highlight was already highlighted by Deshka in his introduction talk. So David Viskan is a Wesleyan undergrad who is now looking for a PhD, by the way, and he wanted to take the sample from Daisy and look at C2 luminosity now as a function of molecular gas mass within each galaxy, to see if you could come up with an alpha C2 factor, as has been shown with observations. And indeed, he can make a fit to the observations shown in black hex bin contours in the back, but we find a much lower alpha C2 of 18 compared to the observations. So this is still work in progress, but I wanted to throw it out there so you know that this paper is coming, and we're still weeding out all the errors. Okay, so finally, I promised just to give you a run through of the new version of Sigame. So there are like three major updates made to the code since version 2 that I'm just going to go through. So first of all, you have your galaxy on the left, and it's showing here surface density of the gas, and at the bottom, position of all stars colored by their stellar age. And then instead of using starburst 99 to estimate the local far UV field, we're actually doing a full radiative transfer with SCIRT. And then the really big part is we implemented this new gas fragmentation scheme. So instead of assuming spherical symmetric clouds, we're using a more statistical approach of using a simulation of much higher resolution as a lookup table for the cosmological simulation. And I'll go into a little bit of detail in a bit about that. And then finally, we have a lookup table as we had before, but this time we're including dust to metal ratio. Thanks to the work of Shili and Deshka, we actually have dust masses in the SIMPA output. So I would say these are the three major updates: the SCIRT radiative transfer, the gas fragmentation scheme, and the DTM ratio that we allow to change in cloudy. So just going into a little bit of detail with the gas fragmentation scheme, I teamed up with Robin Tress, and you can look up his paper 2020, because he's been using a repo to make a replica of the M51 interacting system. And to do that, he used a much higher mass resolution than what's achievable in cosmological simulations. So I took that output from this isolated galaxy simulation and divided it into small cubes, 200 parsec on a side, to estimate what is the density PDF locally within this highly resolved galaxy. And once I had all of these density PDF standing for probability distribution function, so it's basically just giving you mass fraction as a function of density. Once I had those, I binned them in terms of the local SFR volume density and the volume average gas density, because we expect the PDF to change with these quantities, and we can find these quantities in the SIMBA galaxies on similar scales. So doing that, first we tried just fitting a log normal to these mean profiles, as has been done in the past, with a certain width and a center, and that works okay. But if we look into the papers by Blakesley Burkhardt, we actually know by now that at high densities, we start to form a power law tail due to gravitational collapse. And that gives us a much better fit to these mean profiles. Thank you, Chris. 2 minutes. Okay. And then the final step was to add in the gas that's hidden in sync particles. Before the gas is able to form stars, it's temporarily stored in these sync particles. So using this as a lookup table, we could actually get to much higher densities than what's readily available in the cosmological simulation. And these are just some pretty images of 3 galaxies from the SIMBA 25 megaparsec volume. So column 1 is CO120, C2 158, and O3. We compared across 8 different far infrared lines. And I want to just focus on the green bars, which is our default model. And it might not look super good, but we're really happy to see this overall agreement for such different far infrared lines with this new approach. And finally, I just want to mention that I'm also trying to prepare for JWST by moving to slightly lower wavelengths, combining basically SIGMA with powder day to predict PAH emission and infrared, emission lines in the mid-infrared. Yeah, and with that, I'll leave you with the conclusions. So if you have any a project where you would like to use SIGMA, please get in touch with me and I'll be happy to work with you. Thank you.
Fantastic. Thanks very much, Karen. Just waiting for some questions to come through on Slack. But in the meantime, I'll take chair's prerogative, ask my own question. The density distributions, so if I understand correctly, you analytically model them based on these high resolution simulations.
Yeah.
Have you explored other ways of parameterizing the other properties of those high resolution simulations? And how many of them did you have as well?
Right. I'm only looking into this one test galaxy. So we set up the framework to be relatively flexible. So you can use any high resolution galaxy simulation that you want to use as table that you believe in. But yeah, we haven't looked at other ways of estimating the subgrid density profiles.
Okay, thanks. We've got another question here from Il-Sang Yun. The shape of those density PDF depends on Mach number of the ISM and magnetic field. How realistic are the simulations to match the observed PDF in the ISM?
Right, that's a very good question. We did try to plot up the total PDF, or Robin actually has it in his paper, the total PDF he gets for the M51. And it looks sort of what we expect, but then again, it's hard to compare with observations. And you're right, like the width up here directly translates to a Mach number on very small, if you're on very small scale. And I didn't mention this, but in the past in literature, people have just adopted like a Mach number of 10, say, to get an idea of the density distribution on subgrid scales. And I haven't actually looked at the Mach number for each of these bins, so I don't know how much it differs from that default Mach number of 10, but I would assume it does change with the local environment. Thanks, good question.
Great, thanks. We've got time for one more. So Livia Vellini said, very nice talk. Do you plan to study also very high J CO lines to possibly constrain the PDF and the high density tail?
Yeah, that would be, yeah, definitely. That is one of our future project ideas, to look at high density tracers, because the 8 that we tested here do not really probe very high, although CO322 has a high critical density, where we're not talking HCN or HCO plus or something. So that would be really interesting to really test this scheme fully.
Great, thanks. We'll leave it there and move on to the next speaker. Thank you, Karen. Our next speaker is Shenki Yang. Great. So
Hi, everyone. Can you see these slides?
Yeah. So yeah, this is Shenki Yang from New York University, presenting an analytic model for O3 fine structure emission from high redshift galaxies.
Thanks, Chris, and thanks everyone for giving me this opportunity to present my recent work. Today, I want to give a brief introduction about a first principle O3 fine structure emission model that we have published last year for high redshift galaxies. This work is supervised by my collaborator, Adam Leeds at UPenn. And the motivation of this work is that, firstly, as Livia has mentioned before, the recent ALMA observation has yielded a handful of C2 and O3 detections at a redshift higher than 6. And those measurements shows that C2 and the O3 lines are very valuable probes for the epoch of reionization galaxy population. Moreover, there are also prospective interests to map O3 lines in the intensity mapping community. For example, the upcoming spherics intensity mapping survey has proposed to map multiple O3 optical lines in the near future. So motivated by all those observations, we propose this analytic O3 model in order to better interpret the current and the upcoming observational data. Before getting to detail about the O3 modeling, I think it would be helpful if we first go through a brief review about the O3 atomic structure. So the doubly ionized oxygen ion contains in total 5 fine structure energy states. They are summarized in this figure. And the fine structure emission lines that we have covered in this work are highlighted in the red circles. We are particularly interested in those emission lines because the 88 micron line emitted when the ion goes to from level 1 to the ground state has already been detected by ALMA. The 52 micron line is potentially detectable by ALMA in the near future, and these two optical lines are targeted by the spherics intensity mapping survey. In principle, it is pretty complex to model the galaxy-wide total line emission, mainly because the emitters spreading throughout the galaxy may present pretty complex geometric structure. As an example, in this plot, I show a photo of a high redshift galaxy called Y1, measured by ALMA. And from this figure, we see that the galaxy Y1 contains at least 3 clumpy components. Other galaxies may present even more complex multi-component structure. But in this work, we will ignore most of those complexities and assume that all the radiation, the stars spreading throughout the galaxy can be effectively concentrated into a super radiation source shown in the center. And this superstar will create a single spherically symmetric H2 region enclosed by this blue circle. Since the ionization energy to create doubly ionized oxygen is higher than 13.6 eV, the O3 region is in principle smaller than the H2 region. So I show it in this fuzzier orange area. The justification for us to make such a simplified assumption is that if the radiative trapping effect is ignorable in the system, which means the O3 photon emitted at one place within the galaxy won't be reabsorbed by another place. If that's the case, then the galaxy-wide total O3 luminosity is only determined by the volume of O3 region, and it won't be sensitive to the detailed structure of the O3 region. In order to test if this radiative trapping effect is really ignorable, we did multiple numerical tests with the cloudy spectral synthesis code, and the results are shown in this third plot. The y-axis is the total 88 micron O3 luminosity of this spherically symmetric galaxy, and this x-axis is proportional to the volume of H2 region. We find that as long as the velocity dispersion of the H2 ISM gas is higher than 50 kilometers per second, then the galaxy luminosity is linearly proportional to the volume of emitter. It is only when the gas velocity dispersion is extremely low, shown in this red curve, that the luminosity versus emitter volume show this nonlinear behavior. And it is in those cases that the galaxy-wide total O3 luminosity will be sensitive to the detailed shape of the O3 region. We know that the galaxies resolved by ALMA typically have the velocity dispersion among the H2 regions within those galaxies are typically a few hundred kilometers per second due to bulk movement or disk rotation. So through this very simple test, we confirm that the radiative trapping effect is unlikely to be significant, but still it will be very interesting to further test this assumption with detailed numerical simulations. Due to the limited time of my talk today, I will only introduce our model under the low gas density limit, because in this scenario, our model is very simple, but still reflect the overall logic of this work. And for simplicity here, I will take the 88 micron line as an example, and I will assume that this galaxy is spherically symmetric and homogeneous. So the total O3 luminosity of this galaxy can be modeled as the energy of each 88 micron photon, multiplies the spontaneous decay rate, multiplies the number density of O3 ion on the first excited energy state, and finally integrates this term over the volume of O3 region. So two terms unknown in this expression is the volume of O3 and the abundance of O3 ion on the level 1 energy state. I denote it as N1 here. So we can instead solve for the volume of H2 region through the hydrogen ionization recombination balance equation. We can then solve for this parameter N1 through the O3 level population balance equation, where the left-hand side is the rate at which the ion leave the ground state, and the right-hand side is the rate at which the ion goes back to the ground state. Plug these two expressions back to the first equation, and we further ignore the volume difference between the O3 and the H2 region. So after this derivation, we can get a very simple expression for the galaxy-wide total O3 88 micron luminosity. There is one feature I want to highlight here. So under the low gas density limit, we find that the total O3 luminosity is independent of the ISM gas density. It is only proportional to the ISM metallicity and the galaxy star formation rate. This is a very ideal property because the H2 region gas density is not well resolved in either numerical simulation or observations currently. So this simple model can be easily applied to, for example, hydrodynamic simulation or semi-analytic galaxy formation model. In this figure, we compared our model prediction shown in the dashed curves with the cloudy simulation results shown in the solid curves. And we find that the model agree very well with cloudy as long as the ISM gas density is much lower than the critical density of the 88 micron emission line. We further extend our model through three aspects. First, we consider all the possible transitions among the bottom three fine structure energy states. We also use the escape probability approximation to account for the radiative trapping effect within this spherically symmetric galaxy. And we also model the volume difference between the O3 and the H2 region. With those extensions, we find that the prediction of the full version of our model always agree with cloudy within 15% fractional error over wide ISM parameter ranges. And in this first plot, as an example, I show the model cloudy comparison at metallicity of 0.2 solar metallicity. We also test that our model works equally well for the other three fine structure emission lines that I have mentioned at the beginning. In the second and the third plot, as two examples, I show the model cloudy comparison for the 52 micron line and the one optical line. Okay, so the main feature of our model is that it predicts the luminosity versus the star formation rate to decrease as the gas density increase, while it predicts this ratio to increase as the metallicity increase. Therefore, if I compare the current 9 ALMA O3 detections shown in the black crosses with the model predictions under some typical ISM parameter values shown in those dashed lines, basically our model prefers galaxies with pretty high L over SFR values to have either high metallicity or low gas density. On the other hand, for galaxies with low luminosity versus star formation rate values, the model prefers them to be either metal poor or have high H2 region gas density. So based on this feature, we are able to constrain the gas density and the metallicity for all the current 9 ALMA O3 galaxy samples, and the 2D posteriors are shown in this plot. The first thing we may notice here is that these two ISM physical parameters shows this L-shaped degeneracy, which is expected because our model is trying to constrain 2 free parameters with 1 observational data, which is the luminosity versus star formation rate value. But nevertheless, we are still able to constrain a lower bound of metallicity and then an upper bound of gas density for all those 9 galaxies. The degeneracy between these two ISM parameters can be further break by measurement of other lines. For example, in this work, we show analytically that the luminosity ratio between the 88 micron and the 52 micron line is a very good gas density diagnostic. And similarly, the luminosity ratio between O3 optical line and the 88 micron line is a sensitive temperature diagnostic. So we think this model will be very helpful to further interpret or do observational forecast for the future ALMA observation or JWST. As an example, this year we have forecast the detectability of the 52 micron O3 line signal for all the current 9 ALMA O3 galaxy samples, and we find that for galaxies, a significant 52 micron signal detection is very promising for these 4 galaxies with only 2 to 10 hours on source observing time. So we think it might be helpful for people who are interested in writing proposal for the ALMA 52 micron O3 line follow-up measurement to have a look on our most recent paper on the archive. So thank you very much for listening. And from here, I will take questions.
Great, thanks very much, Shenki. We have one question coming in now from Il-Sang Yu. Does your model discriminate AGN and star formation, both of which can produce O3 lines, or does it not care what the energy source is?
So basically, in our model, the Strontium sphere, the radius of the Strontium sphere is basically determined by the hydrogen ionization rate. And from there, we use the empirical model, which is calibrated to the starburst 99 that links the hydrogen ionization photon generation rate with star formation rate. So actually here, this is how the star formation rate of galaxies enters our model, and we don't distinguish the star formation rate and the AGN in this work.
Great, thank you very much. If there's any other further questions, please post them on the Slack, and Shenki can get to them later. So that's everything for this session. We're gonna have a quick 5-minute break to go and top up your CIDER or your Sazerac, use the restroom, and then we'll be back in 5 minutes with Luca Graziani. Just want to say a big thank you to all the speakers so far for all staying on time. Absolutely remarkable, good work. Oh, and Ashwin will be your chair for the final session. Thanks.
Hello, Ashwin, do you hear me?
Yes, I do.
Okay, can I try to share my slides so that I'm sure that everything works? So do you see the presentation in presentation mode or?
Yes.
Okay, let's stick here and wait for.
Yes, everything seems to be well.
Welcome everyone to this last session of the CIDER CIDER. I hope you are having a good time listening to all the talks. There are 3 more talks remaining, and at the end we hope to take a group picture, so hopefully everyone stays behind for at least a minute or 2 for that to happen. So for the speakers of this session, I'll be giving you a 2-minute warning by playing this game show sound. If you can hear me, it's this one. And yeah, that's your 2-minute warning. And the first talk of the session is by Luca Graziani from the University of Rome. He should be speaking about the hydrodynamical simulations with the dust model he has introduced in there, and will be talking about the assembly of dusty galaxies at Z greater than 4. I now give the space to Luca.
Okay, hello everyone. My name is Luca Graziani, and today I'm going to talk about the assembly of dusty galaxies at redshifts higher than 4, which is a recent work I've done in close collaboration with Raffaella Schneider at the University of La Sapienza in Rome, and all the people that you see in these slides, the larger collaboration. So the importance of dusty galaxies is not just a theoretical fact, but it's an observational fact as we observe dusty galaxies in the epoch of reionization, which means at redshifts higher than 6, around 1 gigayear after the Big Bang. And these galaxies appear to have remarkably high dust mass, up to 10 to the 7th solar masses, but at the same time, most of them are regular star-forming galaxies, not starburst galaxies. So the first question is, what is the origin of this dust? And the second one is, what is the chemical evolution of the cold ISM of these galaxies, and how it relates to to the dust presence. And finally, what is the impact of these galaxies on the global process of reionization through their escape fraction? So you have to remember that all these processes have to occur within the first gigayear. So we started the investigation by taking a simple semi-numerical model, which follows the buildup of the dust mass in a Milky Way-like galaxy and all the galaxies in a local group like volume. So as you can see on the left, you can follow the evolution of the total dust mass in redshift. And if you compare the line, the cyan line with the green line, you immediately realize that it's really difficult to make, to assemble the total dust mass observed at redshift 0 without assuming something like a maximum efficiency for the dust hills. The same thing occurs on a population of dwarf or satellite galaxies in the local volume, as you can see on the right. And if you compare the red and the black line, you see that how the predictions for the observed population and the simulated population differ. So the take-home message of this model is that if you try to follow the redshift evolution, it's really difficult to produce the total amount of dust at redshift 0 by just considering production by stars. And the situation is even more puzzling if you go to the high redshift within the epoch of reionization. Mancini in 2015 has done a modeling of the dust production within the epoch of reionization, trying to fit the dust mass inferred by Scherer and Magliorino at that time. As you can see on the right, there's dust, the redshift evolution and the total dust mass assembly. In violet, you see the contribution done by AGP stars. In yellow, the integrated contribution by supernovae and LGB. And in both plots, you see, both on top and bottom, you see that it's really difficult to match the total dust mass by counting only for stellar sources. If you consider other processes, such as dust growth or evolution in the ISM, and you can reach the observed masses, but at the price of assuming very short timescales for these processes. So is this a problem of the modeling, or they really are so short? So we try to apply the same modeling on consistently in a hydrodynamical simulation, creating this dusty gadget code, which is an evolution, an improvement of the standard gadget code, by following the evolution in time of the total stellar mass in each gas particles forming stars. And basically in this formula, you see all the processes acting at the same time. You see that the variation in time of the total dust mass is the resulting of astration plus growth of dust in the cold medium minus processes removing dust either by destruction by stellar shocks or sputtering in the hot phase, plus the usual term, which is the term creating dust from stellar sources. So this model has many advantages, as all the stellar populations are described in detail, separating POP3 and POP2 stars. The IMF can be studied, and the stellar ages and metallicity are very accurate. So consider that each process has a specific time scale, as in the formula, which is regulated with strong function of the environmental conditions in which dust grains reside. So basically you have an hydrodynamical distribution which accounts for different ISM phases. And the result of one possible result is shown here. On the right, you see the spatial distribution of the dust density. On the left, you see the spatial distribution of the gas temperature. And at the center, you see the cold phase of this galaxy, and at the same time, on the right, you can appreciate the high amount of dust in the cold phase, while the dust density decreases in a very regular way towards the outskirts of the galaxy, and the irregular pattern is due to the feedback processes, winds and gas dynamics, moving the dust grains in the surroundings. The isocontour lines show the very irregular pattern of the dust-gas ratio. But it seems that the dust really clumps towards the center in the cold phase. So it's really important to understand this. It's not that an advantage of doing this hydrodynamically is not just that you describe the spatial distribution, you see in space what is the value of each quantity, but you can also study the global evolution of the galaxy population and cosmological volume, as is shown here. From redshift 9 down to redshift 4, we were capable to follow the evolution of the total dust mass as a function of the total stellar mass. These are the blue points, and compare them both with semi-analytic models and all the available observations in each redshift bin. As you can see, our trend is quite compatible with the available observations, and there is a deviation around 8.5 in logarithm of stellar mass, showing that once you have a sufficiently dense cold interstellar medium and a chemically evolved galaxy, you can start having all processes of dust evolution at play, which make this strange transition deviating from the linear production by stars through an average yield. So all this results in this kind of agreement you can take now with standard assumptions on the timescales for grain growth, which means that by adopting hydrodynamical simulations and by describing the timescales of dust evolution, you can really naturally reproduce the total amount of dust. But the problem is when you try to compare your theoretically derived total stellar mass with the observed one. As you can see in this table for a collection of galaxies in the high redshift, when you derive the total dust mass from observations, you have to assume a certain value of the dust temperature, and a little deviation of the assumed dust temperature can cause a large variation in dust mass. So we decided to do a step forward, trying to process our dusty galaxies by RT simulations. In this slide, you see an example. We adopt two different RT codes. On the left, you see a map of the dust temperature predicted by RT square, which also predicts lines because it does relative transfer through dust and gas. While on the right, you see the predictions for different phases of the ISM of the dust temperature and the variation from one phase, from one number density to another. And this is done by SCIRT. We have a modified version of SCIRT, which takes the inputs from our simulation. So it doesn't scale with a gas metallicity, but it just uses the actual dust distribution in space. So it takes into account the clumpiness. So you will see all these analyses in future papers, basically. So let me spend 2 words on a different modeling of the RT. When you analyze the conditions in the ISM, it's not just post-processing the galaxies, but you have to really understand what is the evolution of H2 regions inside the ISM of these galaxies. Because the H2 regions are regions in which the radiation is created, and from them they escape throughout the CGM and the IGM, providing the input for the ionization and the global reionization process. So in this work with Martin Gladsley, we created a version of the time-dependent relative transfer called CRUSH, which is usually adopted to perform large-scale reionization simulations. And basically, Martin analyzed and tried to understand the effect of having dusty H2 regions. And the impact on the ionization profiles that you see in the figure on the left. At 0, you have the source and you have the profile of the H2 region. And you can appreciate how a large amount of dust can really shrink and can have a significant impact on the evolution of a single H2 region. So everything is in place. Now finally we have all the simulations. We have a reasonable description of the total dust mass and a spatial distribution of the dust, taking into account the clumpiness. And we finally can post-process this also with time-dependent radiative transfer codes to try to understand what is the escape fraction of these galaxies and how the escape fraction of ionizing photons, which are the input for the reionization process, is modulated by galaxy properties. So we will have a physical description, hopefully, of the evolution of these galaxies consistently with the process of reionization. So I'll leave here my conclusions, and thank you very much for your attention.
Thank you, Luca, for that nice talk. At the moment, there are no questions on Slack, so I'll ask a question of my own. So you plotted the temperature of the ISM phases in one of those plots. So is that the actual temperature of the ISM, or is this more of a subgrid temperature?
So the point is that the real temperature of the ISM is difficult. I mean, it's really difficult to predict the real temperature of all the phases that you model in a hydrodynamical simulation because of limits of this simulation. I think this is your question, right? Yeah. For what pertains to the hot phase, you have a properly implemented cold cooling function, which depends on temperature, density, and metallicity of the gas. But the problem is when you try to model the cold phase, as the cold phase is not, at least in the Springel 2003 model of ISM, the temperature of the cold phase is pre-assumed as the simulation can predict the variety of very cold phase, warm phase, because it doesn't have any radiative transfer self-consistently included. So at this stage in this paper, we just used the original model. So the temperature of the cold phase is fixed at, I don't remember exactly the value, but around 8,000 Kelvin. So it's on the limit of photoionization. But the answer will come with this last work when we will be capable to have an extremely well-resolved gas distribution in the ISM at the center of these galaxies where the bunch of dust clumps, and we will be capable to post-process, or hopefully on the fly, to process the ISM with proper radiative transfer, describing what is the fraction of H2 regions, what is the fraction of warm medium, following the propagation of the radiation throughout the ISM. And that will be the RT constrained temperature of the cold phase.
Thank you. I'll also ask a quick question from Desika. He's asking, is the spatial distribution of dust within a galaxy driven by the distribution of gas? So what he actually means is that is the dust physically tied to the gas, or does it feel different dynamics than the gas? No, we follow the production and evolution of the gas per SPH particle. So in each star-forming SPH particle, you basically apply this equation. So if you trust the dynamical evolution of the gas, you also have all these grains dragged through the gas and experiencing different environmental conditions depending on their surroundings, their density, and the temperature of the hot phase. So basically all the processes are applied depending on the specific conditions in which each particle resides in the simulation. There is one limit to this, which is the fact we are still following gas and gas metals at the same time. So for example, we don't have a prescription for momentum-driven winds.
as we don't have an exact description of the radiation field inside the galaxy. So I think that...
sorry, I need to interrupt you there.
Sure.
I think we have run out of time, so
okay.
you might need to...
I will finish on Slack.
Okay, so we have our next speaker, Anita Zanella, who's going to speak about early galaxy growth, the contribution of mergers and star-forming clumps. So Anita, if you can share your screen.
Sure. You should be able to see it now, right?
Yes, yes. So your time starts now.
Good. So thank you. Good evening to everyone. I would like to thank the organizers for this opportunity to present my work here tonight. So I will start with a brief introduction to put the work into context and then move on describing some of the most recent results that we have been obtaining. So it is quite well known by now that the cosmic star formation rate density of the universe peaks around redshift 1 and 3, and the formation of stars per volume decreases in the local universe and likely decreases also at higher redshift. But also the appearance of galaxies is different at different redshifts. So in the local universe, Milky Way-like galaxies have this very regular morphology with spiral arms, a central bulge, and they mainly form stars in giant molecular clouds and day 2 regions. If we go at cosmic noon, Milky Way-like progenitors have this irregular morphologies. They don't really show a central bulge, they have higher gas fraction, and their structure is dominated by these bright blue patches, which are massive star-forming regions that are typically called clumps. And if we go to even higher redshift, above 4, galaxies are often showing multi-component systems, and it's still unclear whether these multi-components are star-forming regions or rather mergers. So as I said, clumps are ubiquitous at cosmic noon. They're star-forming regions, but they have stellar masses and sizes 10 times up to 100 times larger than local star-forming regions. And it's really critical to study them to understand how galaxies assemble their mass. Indeed, there have been proposed 2 different scenarios for the formation of these massive star-forming regions. On one hand, they could be merger remnants, so they could be satellites that merge with the host galaxy, ghost stripped, and what remains is a dense nucleus that keeps forming stars. But on the other hand, they could be originated due to secular processes, and in particular disk instability, in the gas-rich and turbulent disks of galaxies at these high redshifts that just fragment and form these giant star-forming regions. So clarifying how clumps are formed helps to clarify how galaxies assemble their mass through cosmic time. And trying to understand what's the origin of this star-forming regions, Shibui and collaborators in 2016 analyzed the data in the Candace fields, and they computed what's the fraction of clumpy galaxies from redshift 0.5 up to redshift 8. So this fraction is determined from UV selected galaxies, and it seems that the fraction of clumpy galaxies evolves as the cosmic star formation rate density that I've shown you at the beginning. So this seems to indicate that these massive star-forming regions are formed in situ due to secular processes. And in particular, these blue points are Lyman break galaxies at high redshift. However, in most recent years, several works have started to show that more detections are found when observing with ALMA, so in situ or dust continuum. So these are just some examples. In the background, you see the HST UV data, and the contours are situ or the dust emission. And there are some components that are visible in situ or in the dust and not detected at UV wavelengths. So in some cases, the UV and situ detections are showing even some displacements. So the question here is, is the fraction of clumpy galaxies determined from the UV at this high redshift correct, or do we need to modify it, taking into account also the situ and the dust detections at these redshifts? So trying to answer these questions, we considered cosmological zoom-in simulations, and in particular, we focused on one main galaxy, that is Althea. That's the redshift 6 Lyman break galaxy. And we considered 2 snapshots. The first one you see on the left-hand side is the galaxy appears as a clumpy disk. On the right-hand side, you see instead the second snapshot where the galaxy disk is merging with a satellite. So that's mainly a minor merger. Starting from these two snapshots, we created mock HST, JWST, and DALMA continuum and emission line maps, and we added observational artifacts such as we convolved for the PSF, we added some noise, and the pixelization of the detectors. So we have models in C2 and band 6 continuum from ALMA, and then we simulated two JWST bands, one from MIRI, the other one from NIRCam, and we also simulated 4 HST bands from the H band to the Z band. And we considered two cases, what we call the low resolution case, where we consider the resolution of 0.15 seconds, which is 750 parsec at redshift 6, and a high resolution case of 250 parsecs at redshift 6. So we created these mock maps, both for the disk galaxy case and the merger case, and we then analyzed all of them the same way that is typically adopted for observations. So I will first comment on the spatially integrated properties of these galaxies, and then move on and discuss the substructure. So what you're seeing here is the effective radius that we estimated for this case on the left-hand side and the merger case on the right-hand side as a function of the observing band. And there are a few things to notice here. So first, in the low resolution case, that are the yellow and the red points respectively, the galaxy is unresolved or just marginally resolved, whereas in the high resolution case, we start to resolve the galaxies. And we also see an observing band effect. So the C2 effective radius seems to be between 1.5 and 2.5 times larger than the optical one. And this is seen even better. This has been seen already and reported already in the literature by several studies. And it's also seen better in this left-hand side panel, where I'm showing the effective radius measured from the C2 maps versus the effective radius measured from the UV maps. So the gray points are data from the literature, and the color ones are our measurements. So the C2 is more extended than the UV, even if Althea seems to be a bit more compact than the typical galaxies observed currently. And there are a few reasons for that we can discuss later on if you're interested in it. And there is a second effect that I would like to mention. So please focus on the plot on the right-hand side, where I'm showing the ratio between the C2 and UV effective radius on the y-axis and the unobscured star formation rate determined from the UV on the y-axis, on the x-axis, sorry. So the triangles here are the sample from Fujimoto and collaborators from the Alpine collaboration, and these black triangles indicate the average of the sample into star formation rate bins. So there seems to be a trend of the ratio of the effective radii with star formation rate. However, if we include the stars, which is the sample by Carniani and collaborators, this trend is completely washed out. So the difference between these two samples is the fact that Fujimoto excludes mergers, whereas Carniani considers them. So we tried to see whether there is a difference in the radius C2 over UV radii in the merger case and in the disk case in our simulations. And indeed there is. The cyan and yellow points indicate the disk case, and the others are the merger case. So clearly more statistics is needed to clarify whether star formation rate trend is in place for disks, but not for mergers. And I would like now to briefly focus on the substructures that have been detected in these mock maps that we created. So again, for the disk and the merger case, I'm showing the number of substructures detected as a function of the observing band. So for the clumpy disk case, no substructure is detected at low resolution, and only one clump is detected at high resolution. So sorry, the empty histogram represents the number of clumps detected at the full resolution of the simulation, which is 25 parsec. Whereas the field histograms are obtained by looking for substructures in the mock maps at 0.15 and 0.25 arcseconds resolution. So in the merger case, only the satellite is detected at low resolution, and some clumps are also detected when we go to the very high resolution. So I would say that the resolution better than 250 parsec is needed to detect clumps and star-forming regions at redshift 6. But there is, again, also an effect with the observing band. So what I'm showing here is the spectral energy distribution of all the substructures. So at optical bands, only the unobscured metal poor and gas poor substructures are detected, whereas in situ, we detect the high dust extinction substructures. And the JWST bands really bridge these two regimes. So the number of substructures detected in optical and situ maps is similar, but very often these detections are not cospatial, and they have a distance that ranges between 0.7 and 2.5 kiloparsec. So at this point, we can compare our results with what has been found in the literature, both for typical field observations and also for lensed observations. So the resolution, thank you. So the resolution that is obtained in the field is typically this 750 parsecs, and in lens galaxies, we can go to better resolutions. So it seems from here, from the literature observations, that 60% of the galaxies show especially coincident C2 and optical emission, and no substructures have been found down to 500 parsecs. And this is really analogous to our simulated disk case, where the disk of the galaxy is shown both in the C2 map and at optical wavelengths. There is the remaining 40% of the sample that has been found in the literature showing multiple systems and multi-component systems. And for half of these targets, the C2 and the optical emission are not cospatial. So these substructures are separated by more than 2 kiloparsec, and they have a spatial extent larger than 700 parsec. So this is instead similar to our merger case, where the disk of the galaxy is detected in both the C2 map and the optical map, but the satellite is only detected in C2. So the distance between the satellite and the disk is 2.5 kiloparsecs, and the satellite is indeed a size of about 700 parsec. So this seems to suggest that the multi-component systems that were currently detected in the literature are mergers rather than clumps. And this is supported by this C2 luminosity star formation rate plot, where again, the stars are observations from the literature, the color points are from Althea, and these circles indicate the measurements for the disk of Althea. So the multi-component systems are consistent with Althea's disk in this plane, whereas the clumps that are these squares here are below the current detection thresholds. So although they seem to follow the C2 star formation rate relation. So it seems the current observations are likely pinpointing to major mergers. And so to go back to the original question, what's the fraction of multi-component systems at redshift higher than 4? Well, it could be that this fraction is rather 40% than the 20% that has been computed in using UV selected galaxies only. So I would argue that resolved multi-wavelength observations are really needed to understand the early galaxy's mass assembly, and that the merger fraction might be a bit higher than previously estimated. One last final point about the possibility to detect star-forming regions. So I would say that very high resolution is needed, and lensing can be a great help for this. So what you're seeing here is a recent exercise that we have been doing, lensing the mock NIRCam map obtained from Althea. And from here, this is the lens map. You can really see not only the disk of the galaxy, but also the individual star-forming regions multiply lensed. And this is clearly similar to the some of the targets that have been observed by Van Zel and collaborators at these redshifts, where they start to detect star clusters and star-forming regions down to tens of parsecs. So I think I'm running out of time. I will leave my summary here and take questions, if any.
Thank you, Anita. A few questions are about to pop up on Slack, I guess, but we are out of time to ask any questions. So I hope you'll answer any questions on Slack.
Sure.
Thank you. Our next speaker is Laura Somovico, and she will be talking about some like it hot dust and high Z galaxies. If you can share your screen now, Laura.
Yes. So, okay, do you see my screen?
Yes.
Okay, perfect.
Okay,
So-
your time starts now.
Thanks. Hi. So let me start with some observations that we have of the dust field continuum emission at redshift higher than 7. As you can see, there are very few. Nevertheless, these observations have been groundbreaking because they unveiled for the first time the presence of dust even in very early stages of galaxy formation. Despite the many progresses that have been possible thanks to these and many other observations at high redshift, there are still some severe limitations in ALMA observation at early times, and they are well summarized in this plot, in my opinion. On the left side, you see the spectra, far-infrared spectra of a low redshift galaxy at redshift 2, whereas on the right side, you see that of a high redshift galaxy at redshift 6. For the low redshift galaxy, you can see that we have in the literature data points widespread on both sides of the far-infrared emission peak. This means that we can easily constrain the dust properties, mass, and temperature for the observed source. However, for the high redshift galaxy, ALMA bands only trace the right side of the spectrum, and generally very few or even a single data point is available. This means that it's very hard to constrain the dust temperature at high redshift. So what is generally done is to assume this a value for this quantity prior to the SED fitting. But why do we care so much about about the dust temperature at high redshift? So the uncertainty on this quantity propagates on several very important galaxy properties. First of all, the dust mass, and this is particularly problematic or at least interesting for very young sources. Here I'm showing a plot of the dust mass as a function of the galaxy age for the observed galaxy by Tamura, Bax, and collaborators at redshift 8.31. You can see that the dust mass that they obtain, I hope you see my cursor, so these pink points, assuming a low dust temperature of around 40 Kelvin, is actually too large to be reconciled with current dust production scenarios, such as supernovae or this dust production model by Asano 2014. However, if one allows for slightly hotter dust temperatures of at least 60 Kelvin, we can produce the same observed far-infrared luminosity with a much lower dust mass, which is then consistent with current theoretical models. Secondly, not knowing the dust temperature means that we also don't have a clear constraint on the infrared luminosity of higher redshift galaxies, and consequently on the IRX parameter. The IRX parameter, or infrared excess, is the ratio between the far-infrared luminosity and the UV luminosity. And as also was shown in the previous presentations, this is particularly important because it is used in the context of the IRX beta relation. And many observations of high redshift galaxies have, especially the first ones where the dust temperature was assumed since only a single far-infrared data point was available, have claimed that high redshift galaxies might be far-infrared faint. So they are actually below local galaxies in the IRX beta plane. However, if one allows for hotter dust temperatures, also the IRX parameter is shifted upwards, and so these galaxies move back in line, and so they are consistent with local galaxies and IRX beta relation. Finally, the lack of constraints on the infrared luminosity also means that we don't have a clear picture of the obscured fraction of the star formation rate at high redshift. And this is particularly interesting if we consider the latest claims that we might be underestimating the star formation rate density at redshift higher than 4. And so there might be actually a flattening of the SFRT due to the contribution of very dusty and very obscure sources, which were missed by looking only at the UV picture for high redshift galaxies. So I hope now I have convinced you that we do care about the dust temperature. And our idea for the method that I'm presenting today was to try to overcome observational limitations by actually constraining the dust temperature using a single continuum data point. So this is the formula that everybody uses to fit the continuum flux, which is this F nu. And once that one has assumed some dust properties so that the opacity of the dust, this K nu, is known, we are left with two unknowns, the dust temperature and the dust mass, which are degenerate. So our idea was to break this degeneracy by constraining the dust mass using the C2 luminosity. So we can write the dust mass as the product of a dust-to-gas ratio and the gas mass. The gas mass itself can be written as the product of the C2 to total gas conversion factor this alpha C2, multiplied by the C2 luminosity. For the dust-to-gas ratio, we assume it to scale linearly with the metallicity, whereas for the alpha C2, so the C2 to total gas conversion factor, we use well-known relations such as the Deleuze relation, linking the C2 and the SFR, and the Kennicutt-Smith relation. What we find is that the alpha C2 depends strongly on the star formation rate and on another parameter, which is the burstiness parameter, which Livia Vallini has introduced already in her talk. If anybody missed it, we refer to the burstiness of a galaxy by indicating her deviation from the Kennicutt-Smith relation. So we're going to have a bursty galaxy if the KS is larger than 1, which means that the galaxy is more efficient in terms of star formation rate with respect to its gas mass. And instead a more quiescent galaxy when the KS is below 1. So for local galaxies where we test our method both for the alpha C2 conversion factor and for the dust temperature computation, we find that these galaxies are not bursty, and indeed they lay on the KS relation. And this ultimately results in larger alpha C2 values, which imply larger dust masses and lower dust temperatures. For higher redshift galaxies, the picture is a bit more complicated because it's very hard to constrain the atomic gas mass within these galaxies. However, there are strong indications, for instance, from Livia's model, and even just if we think that current observed high redshift galaxies are really strong UV emitters and have a very high star formation, that high redshift galaxies are indeed very bursty, with KS values between 10 and 100. Moreover, when looking at high redshift, we have to add another parameter, which is this Y parameter, which is the ratio between the extension of UV and C2 emitting regions. Indeed, there have been several works, observative work, which has shown us that at high redshift, C2 emission is much more extended than the UV one, with a factor up to 3 or even higher. Overall, we find that the alpha C2 values, so basically the C2 efficiency, is lower at high redshift, and this ultimately results in lower dust masses and warmer dust temperatures. So let me summarize in a few words. Our idea was to use a single observation to constrain the dust mass and the dust temperature, and we were able to do so by using the C2 information to constrain the dust mass and the continuum to constrain the dust temperature. There are several quantities that enter in our computation, so several parameters. And while this at lower redshift, this is not a problem because they are all well constrained by data, at high redshift, this might be more problematic, especially for the burstiness parameter, because of what I was mentioning before, and also because for the metallicity, which is hard to be constrained at high redshift. So what we do, what we are left with basically is a large distribution of solutions for the dust mass and dust temperature, which all produce the observed continuum flux at 158 micron. So what we do to actually be able to constrain the dust mass and the dust temperature at high redshift is to add two physical conditions. The first one is that the obscured fraction of the star formation rate, so the one that we get consistently from our infrared luminosities, doesn't overcome the total star formation rate of the galaxy. And the other one is that the dust mass that we obtain is compatible with the stellar mass observed in the galaxy, which is to say that the stars that we see can have produced enough metals so that this dust mass is actually producible, consistent. So if we have to remember just one line from my talk, it would be this one, that we can constrain with our new method the dust temperature and the dust mass with a single observation and 158 micron, even at very high redshift. So let me show you some applications. This is the high redshift galaxy that I was mentioning even at the beginning at redshift 8.31. And Max Tamura and collaborators with 3 observations, 1 detection and 2 upper limits, were able to provide a lower limit for the dust temperature of this source, around 80 Kelvin. What we do instead is to consider the upper limit at 160 micron as if it was an actual detection. And by doing so, we produce this banana shape for the solutions. But actually, what we are providing is an upper limit for the dust temperature, which means that for the first time, we can really constrain the dust temperature of this source between 80 and 98 Kelvin. What is even more interesting is that one of the parameters which basically creates the larger uncertainty in the dust mass and temperature estimates at high redshift is the metallicity. However, we have even said this in this seminar, GWST will allow us to reduce the uncertainty on the metallicity at high redshift. And this is what happens for this galaxy if I reduce the relative uncertainty on the metallicity between, thanks, the observed 80% to a very reasonable 30%. Very quickly, here I'm showing you the same procedure applied to another high redshift galaxy, the Big Three Dragons by Hashimoto and collaborators. And again, you can see that we are perfectly consistent with the SGD fitting in multiple bands. And finally, we have also applied our method to simulations. And in particular, this galaxy at redshift 6.7. You can see that our result, which is shown here by the green curve, is perfectly consistent with the fitting that one would obtain considering 3 mock data points corresponding to ALMA bands 6, 7, and 8. However, it's interesting to notice that if we use the full SGD information, one would obtain a larger dust temperature. And this is because we are driven, in this case, by these mid-infrared wavelengths where there's an excess of emission for this simulated galaxy. And we can understand the presence of such excess by looking at the probability distribution function, or PDF, of the dust temperatures in the simulated galaxy. Indeed, you can see that if we look at the luminosity-weighted dust temperature, we reach even very high values, way above 100 Kelvin. So what is the origin of this hot dust? We have studied this in previous works, for instance, by Behrens 2018 and our work of 2020. And if anybody is interested, I have some backup slides on this. And let me conclude with a sort of advertisement slide. We are now working on applying our method on Rebels galaxies. This is very exciting because thanks to Rebels, we are going to be able to really increase the amount of both C2 and continuum detections at redshift higher than 7 by a factor up to 5 or 6. And what we are doing right now is to compute the dust temperatures and dust masses of these sources and try to study the evolution of the dust temperature with redshift at these unprecedented early times with a large number of data. So I leave you to my conclusions. Just note that here there is the archive link of our paper, and here's my email. This is a graphical summary of our method. If anybody has data that can be analyzed with our analysis and is willing to collaborate, I'm really open to discussions. And I thank you for your attention and also the organizers for this really nice opportunity.
Thank you, Laura. We have a question from Wilson Yun. So he's asking, is this alpha C2 derived to match the KS relation by compensating the C2 deficit in the sample?
What do you mean, in the local or in the high redshift sample? Sorry.
I would expect he's asking at the high redshift sample.
So actually in the work by Caragnani in 2020, they were showing that if one accounts properly for also the obscured fraction of the star formation rate, even the higher redshift galaxies do not show like a significant deficit with respect to local galaxies. So they actually lay pretty close to the loose relation in terms of C2 and SFR. So I'm not sure of if this answers the question. In any case, I can follow up on Slack.
Yep, thank you. There's another question from Chris Lovell. He's asking, in the simulation, what leads to the high temperature dust reservoir at these very high redshifts? Okay,
so do you still see my slides?
Yes.
Okay, cool. So what we did, and we actually studied in our previous work, was first of all, where do we see these really high dust temperatures morphologically and like geographically in the galaxy? And this is in these very dense and very optically thick points with respect to UV, which are nothing less than gyromolecular clouds. So what we did in our paper of 2020, Somovigo 2020, was to model analytically high redshift giant molecular clouds and compare them with local clouds. This is a plot showing the properties of high redshift clouds, the red star, with respect to local clouds. And what we find is that high redshift clouds have a larger turbulent velocity and also a larger pressure. Ultimately, this impacts the dust temperature because we see that basically we reach optical depth equal to unity, so the maximum of absorption of UV much closer to the center of the cloud in the high redshift cloud with respect to the low redshift cloud. So in other words, dust is hotter due to the very compact configuration in high redshift giant molecular clouds. And we then also added some additional effects such as one of radiation pressure, and this conclusion does not change. And indeed, we find dust temperatures which are above 60 Kelvin, even when the dust pressure is included, which basically pushes slightly outwards the dust with respect to the center of the cloud. So I don't know if this is answering. I hope so.
Thank you. I can follow up on Slack. There are a few more questions there, but I guess we have to stop here. I hope everybody can turn on their camera so that we can take a group photo.
Will you say just before you hit the screenshot button, so we have a chance to smile?
You've got quite a few panels to do, so you might have to hold that smile for quite a while, but do your best.
Let's see if I'm actually taking the screenshot of the right screen. Yeah, it's the right screen. Yes. Okay. So everybody say whatever you say in your language for smiling, I guess. Okay, ready? 1, 2, 3. Yes, I've done one, but probably need to keep that pose again because I need to do the next 2 panels. Okay, one more remaining. Yeah, thank you, everyone. It's done.
Thank you, Aswin. And thanks, everyone. This was great. I think it went really well. Thanks to the speakers for keeping the time.
Please continue to use the Slack to carry on discussions and stay in touch or follow up on any questions as well.
Thank you very much.
And if anybody wants to hang out for a Sazerac, I brought the ingredients for myself, but you will have to provide your own.
Thanks a lot for the great talks.
Bye. Thank you.
Bye.
Bye.
Is that Oliver?
Yeah, he just joined in.
Oh, nice.
Trying to teach him early.
Yes, important. Hi, Oliver. Kunne du lige se, hvad far laver?
Peter, der snakker?
Ja.
Jeg har hørt, at du snart kommer til Danmark. Nu er jeg vist ikke afsløret for meget.
Nej, det er fint.
Man kan lukke computeren.
Ja, vi lukker den nemlig.
Hvad siger du?
Ja, han vil gerne lukke computeren nu, så jeg kan lege i stedet for.
Det er i orden. Det kan jeg godt forstå.
Alright. See you, and thanks for a great workshop, everyone.
See you, Kasper.
Thank you.
Thank you. All right, I'm going to log off and have my dinner, but thanks everyone. I think it went really well. Yeah, lots of questions, lots of engagement. So thank you all. Hopefully we get to meet up soon and have a real Sazerac together to catch up.
Yeah.
Try if we can actually use YouTube to edit the videos. That would be actually easier.
Oh, right. Excellent. Yeah, we should probably perhaps have a quick meeting next week just to finalize things or anything for the videos and the photo and stuff. But I think probably got everything together. But yeah, stay in touch.
Definitely. Yes.
Perfect.
Okay.
All right.
All the best.
See
See you
you.
soon.
See you.
Bye.
Bye.
Yeah, have a good day.
Have a good day. Yuri, are you here?
The recording, I think that it is not finished.
Ah, yes. You should.
Yeah, I actually forgot about that.
I'll stop it here.